Okie doke. Here's me walking you through how to do the makeup for the practicum if your practicum didn't go well. The problem looks just like our lab, with a mass on the cart and a hanging mass. And in the first part, we're asked to find the acceleration of the system given a certain hanging mass, given a mass of the car, and a mass on top of the car. So the first thing I'm going to do is choose a system to analyze. What we've done in class that's usually a quick way to an answer is analyze the whole system and look at forces acting from the outside of the system onto the system, because the rope in this approach is an internal force and therefore it just doesn't matter. So the first thing I want to do after deciding on my system is start analyzing the unbalanced forces. Yes, there's a gravity force here and a normal force here, but we know they're exactly equal to each other and they're going to go away, so I'm not even going to bother drawing them in my force diagram. My force diagram will show only the unbalanced forces, and the unbalanced force is going to be the gravity on this hanging bit. So the unbalanced force is going to be the gravity force on the hanging part by the Earth, which of course is going to be 10 newtons per kilogram times the mass of the hanging part, which is 10 newtons per kilogram times 0.07 kilograms, 70 grams, 0.07 kilograms. So 10 newtons per kilogram times that is 0.7 newtons. And that's the unbalanced force on the whole system. Okay, the acceleration of the whole system is going to be the net force over the mass of the whole system. The mass of the whole system is going to be 250 grams, 70 grams, and 500 grams. I'll do it in grams first, just because that seems easy. And the unbalanced force is 0.7 newtons. So that adds up to 820 grams, and 820 grams is 0.82 kilograms. So the acceleration of the system is going to be 0.7 newtons over 0.82 kilograms. Getting out my calculator. And I'm getting 0.854 meters per second squared. So far I've been sloppy around negative signs because it doesn't really matter. I know this part's going down, this part's going right. It's all good. The harder part is something I've never asked you before, which is how much tension will be in the string. Now, tension's an internal force if I'm analyzing the whole system, so we literally can't talk about it and can't put it into the equation because it's never going to create an acceleration. It's a thing pushing on itself. So internal forces aren't going to turn up in this if I choose the whole system to analyze. But if I wanted to figure out something about the tension, I have to define a system where the tension force is an external force. And the way I'm going to do that is I'm going to study the car only. An equally valid choice would be to study the hanging mass only, and you can have some fun by doing the work for that and showing that you get the exact same answer if you're careful. There is one small trick which I'll let you discover on your own, but to study the car only, we have to choose carefully what mass we're going to include and not include. And I think the right choice is, if we're studying only the car, to include the mass of only the car plus what's on it. Again, we've defined a new system of study, which is just the car plus the weights on it, with the tension force coming from the outside as an external force, causing the acceleration. Again, the gravity force and the normal force kill each other off. They don't contribute to the net force or unbalanced force. Another way to convince yourself that we only need tension forces to be like, oh, I'm only going to study the horizontals. The verticals aren't very interesting. Either approach will quickly yield the tension force is the only unbalanced or external force, and the mass of the car and the mass on the car both contribute inertia, both contribute reluctance to accelerate. Now here's the clever bit. A minute ago we found out that acceleration. And if the acceleration a minute ago was 0.854 for the car and for the hanging mass, that's the acceleration for the car. So the mass of the car, 250 grams or 0.25 kilograms. The mass on it, 0.5 kilograms, was given in the problem statement. So these two add up to 0.75 kilograms. Tension force is the unknown. Multiply both sides by 0.75 kilograms. And so I'm going to find the tension force. And I'm getting a tension force of 0.64 newtons. And looking back at the prompt, how much tension? Hint, it is less than 0.68 newtons. I feel good about that. You can stop now if this all made sense. I'm also briefly going to say, a lot of people are going to be tempted to say, oh, there's 0.7 newtons on the hanging part, therefore there's 0.7 newtons of tension. Boom, done. Well, that's why I wrote you guys that hint. That's tempting and misleading. What if there was 0.7 newtons of tension? Oh, 0.7 newtons of tension, 0.7 newtons of gravity force. This would not accelerate. But we know from the lab that it will accelerate. Therefore, it must be true, if I see this thing accelerating down, that the downwards force is bigger than the tension force. So that's a reason why you should be able to know, before you even do any real work on the problem, that the tension has got to be less than 0.7 so that the gravity force is bigger, so that it accelerates downwards. So I'm just going to pause for one more second on the top half where you can see the answer to A and read the question. Showing you again the final answer of 0.64 newtons. Good luck.